like people have generally, even during my masters I had nightmares about this static timing analysis. So this one is static timing analysis. So the first question is, what is static timing analysis? So as the name suggests, static means it's like static in nature, so no inputs are applied. We just check the timing paths here. Based on delays. Okay. And there is one more term that is called dynamic timing analysis. Here what we do is we apply inputs and check the functionality. It's just like simulating a design and checking its functionality, nothing else. So the basic difference between STA and DTA is, in STA we don't apply any inputs, we just check the timing paths based on the delays of the elements. Okay, and in dynamic timing analysis what we do is we apply inputs, check its functionalities, that's it, nothing much, nothing less. So in STA there are two terms. One is setup time, second one is hold time. So if you will ask me what is setup time, generally by definition it's like the minimum time before the clock edge the input must be stable, okay, and it shouldn't change. So this is setup time, this time. And what is hold time? So the minimum time after the clock edge the input must be stable and should not change. See, the input is not changing. I have given an example as well. So what happens if the setup time and hold time requirement is not met? Okay, so let us take example of hilltop. Like there are two hilltops and in between there is some valley or something. Okay, there is a ball I placed. I went to the hilltop and placed the ball. No issues in that. Okay, and I applied some force onto this ball. Now tell me what will be the location of ball, say after 2 seconds. It may be here, it may be here, it may be here, it may be here, anywhere. So whenever this setup and hold time is violated, you don't know what will be the value of input and it will take some time to settle. Okay, and this state, we exactly don't know where our input is called metastability. It's a big headache for design engineers. So let's take this term, remember this term, what is metastability, because you don't know what will be the value of your output will be. Okay, now let us see. Now I have told you the example, definition and all. There may be one more question, from where this setup or hold time comes. Hold time comes. So for this you have to go into this how this flip-flops are made and what are the delays of those elements and all. So maybe next lecture or next to next lecture we can have this a session on this. Okay, so now let me tell you about like this setup time more accurately. So these are two flip-flops, say D. Okay, there is one clock in between. Okay, we are applying some input. There is some intrinsic delay, that is TPD. Maybe some gate should be there, anything may be there. Okay, it's like combinational logic delay. Okay, now see, this flip-flop has one T clock to Q delay. It may take some time in processing from like D to Q, right? Means clock to Q. Once we get the input, the second delay is T setup. We can write it as TSU, setup time, and the third is T hold. We can write it as T hold itself, no issues. This is same for both the flip-flops, and this delay, this is PD due to some combinational delays or something. Okay, now you see the clock is something like this. Input may be something like this. Okay, now at the first positive edge, what will be the value? It's 0. Okay, but after how much time it will take to have this input? So it will be like T clock to Q plus TPD at this flip-flops end. Okay, so this will be something like this. Okay, got it? Now if you will see, the clock is same for both flip-flop 1 and flip-flop 2, and this has a setup time requirement of TSU, right? Now if you will think of this, so see, this delay and plus this delay must be greater than the clock period, else suppose we have captured the input at here and there is a setup requirement, so this delay plus this delay must be less than this whole this clock period. Okay, got it? So this is basically our setup time equation. Or okay, now again if you will see this flip-flops, flip-flop 1, flip-flop 2, okay, TPD, there is like one clock here, input here, input. Now for whole time, this is the clock and this is T hold. So what our main intention is, a new value of input should not flow before this time. Okay, if it will flow before this time, what will happen? While it already has some delays and all, and again like we are trying to push some new input before processing of previous input, it will like lead to meta-stability. You got it? Okay, so what should be the T hold value? It should be greater than how much time the previous input takes. It takes T clock to Q plus TPD to propagate, right? So this is T clock to Q plus TPD. Okay, so this is whole time equation. Now if you will if you will like closely see these equations, you can think of one thing. So what have happened if setup time violation is there? You can simply increase the time period or decrease the frequency of whole this circuit, and you can like get away from this. But if you will see the whole time, there is nothing like a parameter or something. Every value is fixed. Clock to Q, PD, the hold of a flip-flop. So once the chip is fabricated and then hold violation occurs, we can't do much. So this is like very critical issue in setup and hold time. So you need to keep an eye on this. Maybe in the next lecture we will practice some sums on how to like calculate this clock frequency, how to avoid these violations, how to increase the frequency of a design. These things we will take in the next lecture. This is just for your basic understanding. Thank you.